In our 2018 Synlett article, we describe an asymmetric method for the preparation of S-DICHED. DICHED stands for dicyclohexylethane-diol. Both ditched and diped, which is the corresponding isopropyl congener, are highly useful C2 symmetrical directors for the Matheson homologation. The Matheson homologation is an ingenious reaction which allows for the homologation of corresponding boronate esters with lithiated dihalomethane to deliver alpha haloboronates that can be reacted with a variety of nucleophiles like grignards, alkoxides or azides. Upon iterative application of the Matheson reaction, these nucleophiles become the substituents on a growing carbon chain. The use of ditched or diped has certain advantages over the first generation chiral director pinene-diol. For example, both ditched and diped can be cleaved off and thus exchanged more easily than pinene-diol. This allows for a very convenient transesterification to pinene-diol in order to change the chiral director as shown by Cheng and Matheson in 2012. Furthermore, they can also allow for a second stereodifferentiating step, which can lead to extremely high EEs. However, the classical synthesis of ditched requires sharpless bishydroxylation of stilbene and subsequent high-pressure hydrogenation with rhodium on alumina. The high cost of rhodium chloride and the inconvenience of the high-pressure reduction drove us to explore different alternatives for making these chiral directors. The best one was based on Agarwal's insertion of lithiated epoxides into boronate esters. Therefore, commercially available methyl cyclohexyl ketone was first brominated in methanol. The resulting bromide requires no purification beyond a simple aqueous workup, and this compound can be submitted to a variation of the CBS reduction which was reported by Ortiz Marciales in order to generate scalemic cyclohexyloxyrane. This compound is also quite easy to purify by distillation. The oxyrane is then submitted to the epoxide insertion reaction, which we will examine more closely in a moment, and yields ditched after oxidation with H2O2. The material thus obtained can be purified by recrystallization or chromatography, whichever is more convenient for the scale on which it is prepared. To assess the EE of the material obtained, we used a quick Steglich esterification with O-acetyl mandelic acid, and usually we were satisfied to find EEs of more than 95%, although these could drop to 90% depending on the purity of the catalyst. However, recrystallization was also able to increase the EE again. Key to this synthesis is the Agarwal epoxide insertion reaction, for which the chiral epoxide is first lithiated with extremely high transselectivity. This reaction generates a carbenoid which would be unstable at this temperature. Therefore, the reaction is performed in the presence of cyclohexyl boronic acid pinnacle ester, together with a base that is bulky enough not to react with said ester. This leads to the formation of an 8 complex, which can undergo a 1-2 rearrangement leading to an alpha-alkoxyboronate, which can then be oxidized to the desired diol. Drawbacks of this synthesis are the need for 2 equivalents of cyclohexyl boronic acid pinnacle ester and the potential toxicity of the quite volatile epoxide intermediate. But since the preparation of the cyclohexyl boronic acid pinnacle ester and all other steps can be performed without any need for flash chromatography, we found this route to ditched very handy. If you want to learn more about the Matheson reaction, check out our mechanistic video tutorial, or our review on the iterative synthesis of heteroatom rich motifs from C1 building blocks, for which we have also created a video abstract which you can find here.